Welcome back from coffee break, and thank you for being here. 15 minutes early. Right. So, let me introduce David Barnes. We're going to talk about splittings and incomplete equivariance on algebra topology.
Thank you, and thanks very much to the organisers for putting on this event, particularly this conference and stuff on the surroundings. It comes to Sky. So I plan to do some reasonably accessible, tractable algebra. Spend most of the talk doing that, and at the end of the talk, we're going to try to say how that algebraic setup tells you about something in topology that's arguably more complicated, more difficult to access. Right? Motivation comes more or less towards the end, because I mean we can do a lot of algebra before we have to worry why we're doing it. Algebra is just fun. Let's just do some algebra. So, I'm not trying to be contentious and trying to tell what algebra is, but I think you find an algebra is it's about rings and modules, or at least a part of it is about rings and modules. Okay. And then there's this new area growing called equivariant algebra. And it says, why don't we replace modules by Mackey functors and replace rings by Tambara functors? We don't know what a Tambara functor is, it's the ring version of a Mackey functor. You don't know what a Mackey functor is, that's coming up in about 1 minute. Okay. And so the idea is that one says, right, instead of studying rings and modules, let's move it into the setting of Mackey functors, the setting of Tambara functors. And then, to make things more interesting, because there's a bit more variety, we're going to add the word incomplete here. An incomplete is easy. You know what a Mackey functor is? An incomplete Mackey functor is one where you just don't have all of the transformations. You have some of them, but not all of them. Okay. I'm only going to talk about the Mackey functors bit. Essentially, it's all additive, which is a point that will come up again later in the topological side of things. So if only the Mackey functors, I can tell you about those. So I said that we want some transfers. Keep saying transfer. I should probably say induction, right? But Mackey functor's got restriction maps, it's got induction maps. Just in case you weren't sold on the idea of for algebra, I mean, you know, one can do ideals and find step of the Tambara functor. So you can do the algebra examples of algebra in this setting. And there's proof that it's actually sort of new material. I mean, you get really strange things like 3 does not imply flat, right? So equivariant algebra is genuinely different to algebra. It's a new phenomenon that occurs. So, under pretend you're solving equivariant algebra. Right. So, given that you know what a Mackey functor is, and you know, some restriction maps, I said we're going to take some of the inductions. But obviously there's some constraints on what we want to pick, right? And if I have 2 induction maps that are composable, I want to have the composition. If I've got the induction map from H from K to H, I've got all the conjugates. And someone thinks for a bit, and in the end, one works out that actually what you want is a thing known as a transfer system. Okay. To explain this in a slightly complicated way, but the fact that it is partial order means that we have composition. So what I'm saying is the G transfer system is a bunch of maps going between subgroups of G. It's closed under conjugation, closed under composition because it's a partial order, and then we've got this map which we call restriction, right? Which is if I have a map compared to H, I have a transfer compared to H, I can intersect it. You get a transfer from the intersection code L into L. And just because I will use the language at some point, I will say that H1K is missing. And I have a bad habit of saying transfer when I mean induction map and induction when I mean transfer. Just take them as the same thing, it's fine. Okay. So, simple example. Here's one. I pick the transfer from C1 to C2, C4 to C8, and other transfers. This is a transfer system to C8. On the other hand, I pick every map apart from C4 to C8, and I guess we also do C2 to C8. There's 14 of these. So if you like having a little puzzle to do while listening to a talk, try and work out what all 14 possible transfer systems are for C8. It's quite, oh, it's welcome. Okay, so the idea is to define an incomplete Mackey function. We first pick a transfer system. We use the transfers in that transfer system to tell us what induction maps we get.
I have a question. So
Yeah.
this refines the subset relation, but in this one right here, you don't have a map from C1 to C4 or C1 to C8. I thought those are. So does refine here mean that it contains all subset inclusions?
No, it contains fewer.
Okay, so it doesn't refine it, it's like a subset. Okay. Okay. I see.
I mean, I think it's fine to be, yes.
Yeah, okay.
I agree that there might be another usage. Okay. Just some facts about transfer systems, I think they're pretty cool. They're called POSET. And it's not just any POSET. You take cyclic group of order e to the n. The POSET is given by a POSET of rigid binary trees with n plus 2 leaves. And the number of transfer systems, because of that result, is the n plus first concatenated. And I mean, on the whole, if you're trying to do some counting and you get the Kaplan numbers coming up, you kind of know you want at least something, right? And just in case people want to see what the POSET looks like, I mean, it's exactly this. So, when I argue that if the previous thing is called equivariant algebra, I feel that we can call this equivariant common topics. And if you want an expert on this, you should ask Scott Walsh. It's done a lot of work. It's true, you are. He can tell you all about POSETs and how to count and so on. Right. So, transfer systems are how we decide what kind of categories of incomplete Mackey functors we get. Go on. So, what is an O Mackey functor where O is a transfer system? Well, you get a bunch of B groups, you get restriction maps as usual, you get induction maps, but only induction maps when you get K to H in the transfer system, and you get the conjugation maps with the usual rule about these conjugations being their density. If you compose two restriction maps, or two restriction maps look composable, they can be composed with the next restriction. Same for composing two transfer maps, which is why we've got the axiom about composing transfers. So if you can compose two induction maps, then that induction map also exists. And in some ways, the only rule that we have to know is what happens if I do induction and then restriction. Well, that's the Mackey axiom. And if you sort of sit here and you look at, well, what inductions I'm going to get here, this is why we need the transfers in a transfer system to be closed under conjugation and the restriction, which is intersection, right? So in some ways, like if you sat there and stared at this idea of what we need for the Mackey axiom, you'd get what we need for the transfer system. Right? Oh. So let's go on to just a simple example. It's always a bit nerve-wracking because this is a back of the end calculation I did before the talk. I've got the rest of the page. But I hope it. So the idea is the following: if you have a Mackey function G, one that's got all induction maps, you can just forget some and you get a complete Mackey function. Right? So you've already got plenty of examples. I mean, here's the representation ring. I don't know how to sort of write good notation for these things, but I mean, it's the 6. So you just take the rotation by 2 pi by 6, 4 pi and so on and so forth. So you get the usual representation into each place, hopefully. And then I've just taken the transfer system where I'm allowed to transfer from C1 to C3, C2 to C6. So in the Lewis diagram, you just have a reduction map here and an induction map here. Okay.
What's the delta?
Sorry? sign representation. So you can argue this is very exciting. It's just saying, well, we're going to forget that some of these things are induced here, and some of these things are induced here. Oh, but it's an example. And that reminds me, the conference, I mentioned the representation room, so I think it's fair to say that I can click off representation. I'm sure there's more to it. Let's do a more interesting example. Let's have a look at incomplete Burnside Mackey. So you pick one, pick a transfer system, okay? And then you say, right, we're going to take I want something like the Burnside ring, so it's additively generated by H mod K, but only when K maps to H in the transfer system. So only when I get a transfer, either this is admissible, do I take these things, and then just do the usual things. So I take these finite H sets, and I take the group completion of these things, and that gives me okay. Restriction maps, and then restriction. The fact that I can restrict this and still get something admissible is again visible in the axioms of the transfer system. Indeed, if you wanted to do this, when you sat down and what would I need, you'd get the axioms of the transfer system. So, I mean, the point is the transfer system is tightly controlled by other things. It's not something that's made up on the spot. It's there, and it has to be that. Induction is quite fun. Like, if I wanted to induce from the value of this thing at K to H, right? That means I'm assuming that I've got K to H in O. But at the K level, I'm saying that I've got K mod L, so I'm saying I've got L to K, I've got K to H, and that gives me L to H in the transfer system. So the fact that induction works is exactly composition in transfer system. And then I said the conjugation is just conjugation. Good. Okay, fine. Yep.
Can you say one more time, what does H mod K in brackets mean?
Oh, so take H mod K is a finite H set, and then you take the ring with these as the additive basis. So the growth and the ring. Yeah.
So that's what we're writing as Z bracket things on the previous slide.
Yeah, exactly. Yeah. So take disjoint union as your addition, and then just formally add inverses and the square brackets, which remind me that this is sort of like the additive basis. Right? Okay. Well, we actually get a couple of interesting facts. The first one is, I mean, given G and O, I do have the usual Burnside ring Mackey functor, but that's not the same thing as this. Right? So this is something that only exists in the incomplete case. As far as I can tell now, I just wouldn't know how to extend this to the complete thing. So in some ways, this is new. It will only make sense in the incomplete setting. If you try to do this in the complete case, you're not going to have enough inductions. And so you're not going to have enough information to get the inductions. And then the other one is, you can define a box product on O Mackey functors. This gives you a monoidal structure. The unit for that monoidal structure, O Mackey functors, is the O Burnside. Right? So it's kind of makes this sort of a fundamental example, a key example. This is sort of the monoidal unit of this category, and it is different from monoidal unit of the complete case. Okay. If you like, you can think of this as the ground ring in equivariant algebra when we've taken the transfer system apart. And again, for every transfer system, you're going to get a different category that you've actually been doing. So, write this out as a Lewis diagram. Again, I'm taking this transfer system for C6, where I just transfer from C1 to C3, C2 to C6, and you just get the form. Right? Okay, so You get these examples, they're different. There's sort of new things that are occurring in the complete case, because this is not an example in the complete case. All right. So that's the setting. What do we want to do here? Well, student John Grievance, so it's 15 minutes into the talk, it's about time I start saying, let's make everything flexible. By rational, I just mean that, you know, the leading group is going to be a rational one. If you want, we just take whatever you've got, and it's reduced. There's plenty of examples and so on. We just got rid of torsion, makes everything more difficult. So what happens in the classical case, right? Or if you like, a complete transfer system where you've got every possible transfer and every possible induction map. Well, rationally, that you've got to split the product of bar groups. So for each contingency class of subgroups H, take H. Take a normalizer affecting G, and quotient that by H to get the bar group, and then just take rational modules over that. Okay, so the same simple, it splits. Great. Makes it very simple. Proven independently by two different sets of researchers for different purposes. So, what's going to happen in the rational incomplete case? That's the question, right? And welcome this with Mackey on Mackey and Algebraically. What possible splittings occur? And I mean, we don't expect to get a complete answer, right? Because we know that if you take actions and transfers at all, you're going to get coefficient systems, and then we're going to have splittings in general. So we're expecting a kind of messier answer in the future, right? You'll get some splittings, but you won't get a complete splitting, and maybe the split piece is going to be harder to understand. Maybe it's going to be harder to say, well, it splits into these three bits, this bit is this information, this bit is this one. So we expect to get less in general, but we can still try to do it. So how is this splitting produced? And one way to do it is to say, right, well, what's the ground ring of rational Mackey functors? It's the rational Burnside ring, and we know about idempoteness of the rational Burnside ring. Again, an idempotent rational Burnside ring, is ground ring of a normal unit. An idempotent rational Burnside ring is going to split the whole category, and that's what the splitting is. So it's first of all, take this, it splits up over these conjugacy classes, and then we identify the split pieces. So, in our case, what we have to do, let's take the rational O Burnside ring, and we take it at G. So we're looking at those G mod H's where H transfers to G, we're looking at the rational ring of this thing. And we're saying what splittings do we get here? Because if I get a splitting of this ring, it's going to give me a splitting of the rational Burnside Mackey functor in the case, and that's going to give me a splitting of the category. Yes.
What's the product? I mean, how do I multiply G mod H and G mod K?
Check the product.
The product of sets.
Yes.
Okay, so it's commutative.
Yes. Oh, yeah. And then you've got to say, right, well, how do I know G mod H and G mod K are admissible? How do I know the product is going to consist of admissibles? But again, that follows from the actions. Yeah. Okay. Good. So we're going to fix the transfer system, just to make things, right? Because I mean, this is all sort of one at a time, right? We're not talking about changing transfer systems yet. So each thing is about fix the transfer system, look at what happens there. And so we have this new idea, right? And in a moment you'll see that you go, oh, that's the obvious thing to do. Just for the moment, we're saying that J and K are inseparable if every H that transfers up to G, the size of the J fixed points of G mod H, and the size of K fixed points of G mod H agree that every time I have H transferring to G. This is an equivalence relation in subgroups. And we're going to write square brackets to take it to class. Why do we do this? We do this because it gives us a rational isomorphism when we take the mark on. Right? So what am I doing? What is the thinking here? The additive basis here is those G mod H where H transfers to G. Okay? So then I say G mod H is sent to the thing, which place J takes the size of G mod H, J fixed points. Okay? And I mean, again, I'm describing this as the additive basis, and then you're allowed to make sums, formal inverses, and then you can formally multiply things by rationals. And exactly the same proof as in the complete case tells you that you get exactly an isomorphism here. Right? And if you know the mark on the morphism, you say, oh, it's obviously this thing. And so then we just say EH is going to be the idempotent corresponding to factor square root. So all I'm saying is for every separability class, I get one idempotent.
So conjugates are in particular separate.
Correct. So these idempotents split and first of all, incomplete Verso ring G, but in particular, using the restriction maps, they give you a splitting of the incomplete Verside of Mackey functor, because that's a normal unit, they give you a splitting of the whole. So a couple of steps, that's fine. The point is, I get a splitting just like this. Great. So we understand how this goes, and we've got a description of what these idempotents are, and there's some formulas, and in the abelian case, these formulas are readable, and in the non-abelian case, yeah. So the point is, great, we've got the splits. Fantastic, very happy. One thing to note is that, I mean, this splitting only cares about those things which transfer to G, right? It's only looking at sort of transfer to the top group. The other transfers just don't play a role in the splitting, but they are going to play a role in the structure of what these pieces are going to look like. So, now that we've got the splits, we can ask the next set of questions. How on earth do I describe this without using the idempotents? Because, I mean, yes, I can split something, but actually calculating what this is in general isn't going to be so easy. Is there a more intrinsic description of this category? Again, in the complete case, it would look just like this, but in the complete case, this term would just be the same as rational WGH models. Complete case, these things have a much better description. What can we do to get towards that? And then, what about projecting, injecting homological dimension? And what's going on with the homological dimension? Right? Again, you get to G-spectra at some point, you're going to want to do some calculations. You're going to want to do some homological algebra to tell you what's going on with the homotopy theory. So let's try and sort this out now. And again, in complete case, this is all trivial. It's QWGH modulus. And it's projected, it's injected. Okay. Let's have a look at some examples of this. Here's the Burnside ring for, again, C6, the specific transfer system. We just C1 to C3, C2 to C6. Here's what the battery function looks like for the Burnside ring. And here's how it splits. So I mean, this is a piece, and then sort of imagine a line down here, and here's another piece. Right? And it splits into some of these two pieces. Okay. And really what we're saying is, look, here's one of the idempotents, here's one of the other idempotents, because they're going to transfer from C2 to C6, that gives me an idempotent. So one minus that idempotent gives me the other piece. So we're expecting two pieces. And on this side, you see you get some zeros, it's a bit, but I can split it. Right, I'll burn something back. No one's actually trying to copy this down, because there's no way they're going to have it.
Can I ask a question?
Yeah,
Why do I only see 1/3 here and not 1/2? Because usually when you do this kind of business, you have to invert the order of the group. Like you seem to only need it to invert 3 and not 2.
exactly. Good. So, yeah, I think the splittings are going to happen more widely. I mean, here, I mean, it's an unusual thing where you want for things to have virtual size 1 or virtual size 0, right?
Like,
But yeah, one can probably get away with not using the full range, right?
maybe you just
It's a
use
good
the
point.
indices, maybe you just use the indices of those.
Yeah, exactly.
I see, great.
Yeah, you could probably play a game where you say, right, for this particular transfer system, I only get these idempotent, so I only need these primes to be invertible. It's very difficult. Okay. So if that was specific, Burnside Mackey functor, we can go on to a general Mackey functor. Okay. Take a general M for C6 for this transfer system, it splits into these. It increases M hat, and then like M2. Okay. And I mean, just to be clear, these colored maps, this restriction on the left, and then the other restriction on the left, and this restriction here, they do not need to be isomorphisms. In fact, this particular bit here, this particular restriction on the left from the C6 to the C3 term, this is entirely determined by this blue term, right? That's not clear. I mean, you have to put a some effort to think about it. What this means is that if I want to say, what do I need to remember from N, having split it, to be able to recreate it, all you need is this following information. So this is the one split piece, this is another split piece. You need the value of this group, value of this group, M hat, this value of this group, which again is the split piece. You need to know about the restrictions, you need to know about the group orders. So it's kind of a fair bit to remember, right? Compared to the classical case where you're just looking at the QWGH model that was EH on M. But again, you can split, you can reduce it down. This is all you've got to remember. Another example, but a little bit quicker. So now we're going to take C8, the transfer system where I'm allowed to transfer C2 to C4 and C2 to C8. So again, I'm going to get one idempotent coming from this, and then one minus that idempotent. So I get two split pieces, and the splitting looks like this. And again, I'm not asking you to sort of take it into any greater detail. It's just sort of the top bit splits. The bottom bits are divided into what we had originally here in zeros on the right, and then everything labeled in blue is what we need to remember to recreate the whole thing. Like all this information up here, sort of freely generated from this information here in this first space. Okay. And then finally, if you just take the transfer from C2 to C4, you get no splitting response. This is the, this is the Burnside Mackey functor. Standard people ask, well, does this induction here not give me sort of an idempotent here that I could use to split this term? And the answer is yes, but it doesn't split the whole cache, right? So you might get an idempotent in this ring, but it's not strong enough as an idempotent to split the whole cache. Okay, good. I was wondering, so should you give people a little break, let them just check their phones, relax, would you have to actually I mean,
We are checking our homes anyway, so we're.
they will be the exam at the end. Okay. Right. So how on earth am I going to get a description of these split pieces? Right? Because it's great having like components, they can just be on most apply this category, but I'd like to see it in a bit more detail. Right? Okay. So Mike Hill complains whenever we call it the Burnside category, and he says, no, it's the Lindner category. So I'm going to call them Lindner categories, and I'm not going to get an answer with Mike Hill in this. So
What's his motivation for that?
it's too afraid to ask. So I said we can put the Burnside category. Okay, right. So we need to do something slightly annoying. I mean, transfer systems are really great, a really compact description, but sometimes you need to kind of spread them out a little bit to get a bit more information. For those in the know, what I'm doing is I'm going from a transfer system to an indexing system. Right? Okay. So why subcategories? That means all objects are finite G sets where the map here is in this, if and only if this condition here. Right? And what I'm really saying is when I've got K to H in the transfer system, I'm going to take the map G mod K to G mod H, right? Just a standard projection. I'm going to take these maps, and then I'm going to sort of expand from, right? So all objects, these maps, close your products, pullback's a bit complicated because you're allowed to pull back along any G map. And so I make this category in GO, okay? From the admissible sets, I make thin GO. And now I can define the category, then the category of O, the finite G sets, and morphisms, the article span. So the usual Lindner category, Burnside category, as you imagine. And if you know this, you know that this left-hand map is about restrictions, and the right-hand map is about inductions. And the whole point of this process is to say we're only allowed certain maps here. And these certain maps are determined by the transfer system. I really want to say, oh, we're just only allowed to take sort of G mod K to G mod H when K to H is in the transfer system, but you have to kind of make it a bit more complicated than that, which is a problem. Okay, so this category, it has a category called byproduct, and it's free additive and all the rest, all these wonderful things. Why do we introduce this? It's the same standard thing as in the classical case, which is if you look at product preserving filters from this category to Z modules or Q modules, you get nothing. Right? So the description I gave earlier is explicit, here's a series of maps, you can describe it as product preserving filters of this type. Correct. Good. So now we sort of do this again. I'm going to make another one of these categories. And now, so it's going to be called AHO. And the idea is that when you're defining it, the objects, the spans that you make, using G sets where the stabilizability is subconjugate to H. Right? So I'm just kind of restricting. I'm saying it's G set with stabilizers inside H. Then it gives me a category, and I can do the whole product preserving functor things to Q modules. And I look at these things, and then I have to stick in one more condition, which is I ask that I don't want all possible functors, I just want those which are zero outside of this inseparability class of H. So I'm doing two things. I'm taking the usual category for the incomplete things, I'm restricting the category slightly, and I'm adding in this sort of requirement, nullification requirement. So the whole point is that you get a description of this category in terms of product preserving functors. Okay. I mean, you can do this integrally, of course. It's just, you know, this term only exists rationally. You could look at this integrally if you liked. So it has some advantages, even if it's sort of a bit sort of obscure as to why that's so exciting. Okay. This line here is going to come up again in the topology code. So this is the half of how we can take it from algebra through to topology. That's right, yeah, please.
So. Because like in the usual case, this industrial controversy class page, then you get the automorphism group optimization, and you end up with the Weyl.
Exactly.
Why can't you do with this in this case? How do you just take automorphism of H in this linear category? Describe it as modules already, or something?
Yeah, but I mean, I've got a part over H, but also with the spinning back, I have part over K perhaps as well.
I think that's
Right, and then in the split pieces, sometimes you would have just a restriction map, or you could have a split piece that's got restrictions and then some inductions inside that split map.
okay.
So we hope there's going to be a further simplification, right? But
Yeah. Okay.
good. Yeah, 35 in. Why on earth am I doing this? I'm doing this because I care about equivariant spectrum. Equivariant spectrum I'm hard to work with, which is why we want to look at equivariant algebra. It's easier, it's simpler, it's more budget. And what really kind of starting from this transfer system things is transfer systems correspond to an infinity operads. Right? Any infinity operads are this thing that we're introduced to kind of work out the different possible multiplicative structures on equivariant ring spectrum. Right? In fact, rather than just doing it on the multiplicative structures, right, you can actually do it on the additive structures. So given an infinity operad, or if you prefer saying given a transfer system, you can make a category of O spectra whose homotopy groups are O Mackey functors. Okay. So there's no multiplication going on here. It's just that infinity operads are most familiar to us in the multiplicative structure of equivariant ring spectrum. I mean, the way I think of this is, I mean, to me, would have been much more sensible if we did on the additive case first and then the multiplicative case. But I think it's one of these ones where there's no point learning to walk until you've seen how exciting running is. So, every transfer system gives you a category of O spectra, right, which are G-spectra, but you only allow certain transfers and so on and so forth. And when you take the little disks operad on a G universe U, then O spectra is just orthogonal G spectra indexed on that universe. So these transfer systems extend what we originally counted as incomplete G spectra, we would take in this incomplete G universe. Okay. So we wanted to understand O spectra and how they're fractionally, how these things split, and that was pretty tough. Okay, so well, let's go do the algebra bit first, understand what's going on there, and then try to pull this back through to topology. Right? I mentioned topology, spectra, so I can tick that out of this. Okay, good. Right. So what's going on in O spectra? So I picked finite G, I picked the transfer system O for G, and that gives me a category of O spectra. Right? The monoidal unit is the sphere spectrum, self-maps of the sphere spectrum are isomorphic to the O Burnside ring. Right? And well, the same argument applies. I've got all idempotence in the rational version of this, and I've got rational idempotence here. Rational idempotence in the endomorphism of the unit of the monoidal category, so I get splitting by the same sort of categorical algebraic construction, and so you get exactly. Essentially, this requires no additional work over the algebraic case.
Why is there no Q on the right hand side?
Sorry?
Why is there no Q on the right hand side?
Because I forgot to type it. But yeah, you should definitely be less. Thank you. It's my attention. Okay. So now we get the same question again, right? I've got the splittings. how do I understand this part in nature of rational O spectra, sort of more intrinsic? Because again, using these isophotos, like they're very theoretical tools to only get splitting, but to actually work with it, it's kind of tough. So the rest of this bit is now joined with Mackey, Duran, and Bowman, who were brought in to tell us how to build G-spectra in the right one and everything. So here is a theorem telling you how to go from the linear categories, which we previously used in the background to the spectra system. As I was down at Smith as a student of Mackey. So again, find group, pick a transfer system. I want to make O spectra as an infinity category. And what do? I take this infinity category version of the linear, incomplete linear category. I look at the infinity category with product presented functors from that, right? To spectra. So it's the same construct as Mackey functors, you just have to say infinity category enough times, right? And I mean, my understanding of what this is the following. I mean, I just take the usual category of finite G sets, I then put spans, but instead of taking equivalence classes as spans, I'm gonna treat it as a 2-1 category. So now I can go to an infinity category of this, where what's level n is like n on zigzags, right? And then your simplicial maps are extending trivially, composing, making a particular choice. And it's the choice of how I make the pullback, right? Which is why we need the equivalence class that gives you the infinity category structure, right? Great. So we can play the same game last time, right? In this incomplete thing, which is kind of built from the admissibles. So if I have K to H, I'm allowed to take G mod K to G mod H in O. And now I say, let's take that, but let's only work with sets whose stabilizer only point is subconjugate to H. Right? Well, I can do the same thing. I can make an infinity category version of that. And now, we're just making more and more categories. I do one more thing, which is I take sort of the same thing, but strictly less than H, where now I do the same thing, but I ask for stabilizer not in the inseparability class of H. So here I'm asking it's subconjugate, here I'm asking it's subconjugate and not in inseparability class. Okay. Good. Why do I do all that? Oh, which infinity categories? I think that counts as 5 structures. Bingo. Okay. So the whole point is to get to this, right? And now I'm looking at product preserving functors from here. We're taking the strict version of the category, Q module. So this is in algebra, right? So here's the sort of the H part, and then say let's restrict to those things which are not in the inseparability class. So let's look at the kernel of this. This kernel is exactly what we described here, right? In the, instead of working with just a O, I restricted to the H part, and then I required that certain things were 0. So taking the kernel is requiring things are 0. So what we're saying is we have restricted from a category to this subcategory, and then put on that condition here. Why is that so very helpful? Because subsequent theorem, we've not quite done it, but we think it's a bit low. You can just extend this to the infinity category level, right? I replace Q modules by rational spectra. I replace this by its infinity category version, right? The Record structure, instead of being an actual record of algebraic categories, becomes a record of infinity categories. So the whole structure should be read. So, a couple of points. This structure exists integrally, right? I mean, I just put Z modules here and get like the flavor of Mackey functors and something else, a bit of Mackey functors here. But the splittings that we were originally working with should only occur randomly. Right? And why do I want to do this? I mean, one of the first things people ask is sort of, why don't I just try to split this category using the homotopy? And then the simple answer is it's not quite hard to complete. You can't do the splitting. One way to see this is, I mean, it's got a terminal object G mod G. Well, you can't split G mod G in that category, right? It's just a single point. There's no smaller something it can be. So you kind of need to make things either totally complete before you can apply the splitting. Roughly speaking, that's pretty much taking functors to cube modules, right? So how would you want to do, try to make this either complete? Well, patience is kind of the answer. Inside this Tate construction, there's a bit that one can make that's called the Tate piece or the Tate data. Right? And we think that we'll be able to extract that from the setting. We'll be able to say that that Tate piece is exactly zero when we're rational, or it's partly rational depending on what primes we need to revert. Right? And you'll actually be able to really sort of get at why this thing splits rationally, why does it split integrally. So strictly speaking, we should be able to do this without using the idempotents. But I mean, again, the point is that you want to say, well, what's the easy method of splitting? Idempotents. What's the more complicated method? Doing a bracket one, either at the algebraic level or at the infinity category level. One more thing that we think we should be able to do is, I mean, in some ways, these categories and AO in general, one can actually start to say, well, what is this thing? What properties does it have? And I mean, there's already an extension of these things called equi-orbital categories, where you say, right, well, what properties does something like a finite G sets G-equivariance have? Let's extract that to some pretty esoteric category theory. Excuse me. And then we think that we should be able to do a similar kind of story, right? That you sort out in the algebra, and then you work out what's going on, you get the splittings, you get the understanding, and then you lift this to the level of spectra, sort of essentially buy a machine, buy this kind of reference, or buy this kind of setup. Okay. So a bit of a sum. Right? I mean, I take this as the algebra first approach that we've seen in the equivariant homotopy theory before. First, you work out what's going on with the algebra, and you do so pretty carefully, and then you attempt to lift that algebraic description to the setting of G-spectra. And then there's a bit of art on trying to work out what structures are going to be able to lift. That's why we spent some time setting up the linear categories and then looking at these kind of smaller pieces in order that we can lift the splitting straight away. And in general, I emphasize the idea of in trying to do something like equivariant homotopy theory, try to sort out the algebra first, is the good government. In fact, we try to kind of do this splitting and understand it in the case of incomplete universes anyway. And we can't just run around. I mean, you're trying to do these sort of standard calculations that people have done in the complete case. But, I mean, you've got to worry about what vertebrate multiples do I have to be in universe. But that's kind of, you kind of got to worry about atomic speed and then the atoms of the small business. Trying to get all of that from existing literature stuff. And I mean, again, you're only going to be able to do the case of incomplete GPU universes. You're not really going to get any other infinity parameterized versions of G-spectra. So we were very happy with this. By doing it in this way, you transfer the problem from something that's pretty tough. You know, if you're working with G-spectra in the sense of NMS or EKMM or something, you translate it to something much more combinatorial using, for example, techniques of the category. And then you're actually able to answer the kind of questions with some context, with some outcome. Okay. So we were very pleased that this method allows us to get at the problem much quicker, much more directly. So sorted out the algebra, split it into homotopy theory, and one of the things we're working on is the homological algebra in split pieces. We've got some interesting questions, we've got some very early conjectures. The Fertilli subgroup appears, which pleased us all greatly when that came up. And I think I've only really got one more thing to say, which is that this is all sort of work in progress. It's all ongoing, or perhaps I should say, the work is incomplete.
If I understand correctly, that in your definition of the start side, a linear categories or linear categories, the equivalents are usual isomorphism.
Yeah.
So they do not incorporate inseparability inside it. So you can have inseparable things which will not be isomorphic in your category.
I assume, they're going to be isomorphic. I assume they're going to be inseparable. I haven't directly checked. Right?
So you're saying if they're inseparable, then they will be non-isomorphic. That's all.
No, you're saying, so you're doing this span and you've got a thing in a bit of T, you've got that isomorphic as a G set to T prime.
Yeah.
Right? Then I believe that the things that are made up from the first one will be the same, in the same inseparability class and things making up T prime.
I
Yeah, right.
yeah.
Any more questions? I have one. Actually, maybe one and a half. So it's very naive. So back in ancient history, back in ancient history, there was a work of Peter Weyl on splitting, stable splitting of classical experience in finite groups using exactly those, well, not exactly those techniques, but Mackey functors, etc. So how does that does not require the existence of the present for finite groups, everything is at once.
Is the one where you get idempotents corresponding to perfect sums?
No, well, that was part of it, but the whole bunch of papers about stable splittings, which we continue to really use as well to prove some things, but the single conjecture can. So how is it related? In particular, we are doing here everything in Russian, but this, Mackey functors does not require Russian. So, how does it feel?
So I'm afraid it's an excellent question, and the answer's a terrible one, which is I don't know. I'd love to hear more and have a look. I just don't know. Let's talk some more.
Any other questions? Right, then let's again.